We are now in Chapter 6, Applications of N2L. Maybe I shouldn't say N2L. It's primarily N2L. You do have Newton's third law. You do have Newton's first law. So there's a lot there, okay? First exam is after this chapter. I have an estimate in the calendar, but assuming that we keep to that calendar, that's where we're going to be at. Okay, so what I want to do here is that what am I going to apply here? What I'm going to apply is this thing right here. These are my strategies. Okay, these are my strategies. I'm going to always look to see whether the object is accelerated or not. Once I figure that out, then it's telling me how to draw my free body diagram. Once I got my free body diagram, I break the forces along the components like I talked about. But the big difference now is that what are we going to do? We're going to solve two equations. The vast majority of the time, Newton's second law set up two equations, two unknowns, and that's what we solve. So that's what we got to go after. So let's go do it. So the first thing I want to do, I want to go get our first example, and we want to start jumping on this thing. So here we go. We're going to apply Newton's second law to this example here. There's a lot in this example. Okay, there's a lot in this example. So let's see if I can do a good job on this thing here. So what we want to do here is that we want to look at this thing carefully now. Okay, let's read it. So it says an elevator with the weight of 27.8 kilonewtons is given an upward acceleration of 1.22 meters per second squared by a cable. Calculate the tension in the cable. Okay, calculate the tension in the cable. So what do I really mean by this here? Well, for starters here, the thing that we want to look at is that we imagine that the first thing that I would do here is, this is a red flag right here. In other words, note the mass is not given, but the weight is. Remember, we do not use weight in Newton's laws. We use mass. So we can actually calculate that because the force of gravity, which is mg, that tells us that we can get the mass of the elevator by looking at its weight divided by the acceleration due to gravity. So remember, when I write G is 9.81 meters per second squared, not minus 9.81 meters per second squared. This is a no-no. Do not write minus in G. It is the magnitude. So you got to be careful about that. So here we go. So what we want to do here is that it's got to look something like this. We're talking about an elevator. So, I have an elevator. And there may be somebody in there, but we don't care. Because we're not talking about what's happening inside. So now, here's our cable. The only thing we know is that this thing is accelerating. So that means if it's accelerating upwards, we know that it has an acceleration of 1.22 meters per second squared. So we know that there's an acceleration. That immediately tells us that we now have what? A net force in the upwards direction, right? A net force in the upwards direction. So now, what do I know? Well, I need to be careful with my language here. And I want to know, how should I write this thing? Because we're going to have to be talking about tension up, tension down. I don't know. I should be really careful here because this one is about going up. And if you look at B, there's tension when the elevator is going down. So maybe a good choice in language might be the tension going up and then the tension going up. So what we're going to see here is that we could then go in and let's look at our notation here. So what I'm going to do here is that, how am I going to write this thing here? Okay, here, let's look at this thing here. First thing I'm going to do is I'm going to do my free body diagram. Remember, what happens if you don't draw a free body diagram? I'll probably take 40% off of your problem. And you can complain, and I promise you, it's gonna fall on deaf ears. Free body diagram every single time. Here I go. So now I'm gonna focus on the elevator. And I'm gonna say that elevator is now a dot. What is causing this thing to accelerate? What's the common response? It's the tension in the cable. And what am I gonna say? Hogwash. So the tension going up must be greater than the force of gravity coming down. And from now on, I'm going to stop writing force of gravity. Every time I write that, it's going to be mg. Note that the tension up is greater than the tension down, than the force of gravity down. So therefore, this thing is accelerating. So now I'm going to write down Newton's second law. So note that in this case, it's clear that there's no x's, so I don't need to write x's. But because the velocity is in the upward direction, that's positive. So now I'm going to write my N2L equation. So now the force in the y direction, note I did not write the force in the x direction. That must be what? Positive T up minus the mass of the elevator times g. Look at the minus sign. Why is there a minus sign? Because g, the force of gravity, is pointing down. And then this must be mass times acceleration. What causes this elevator to go up? It's not the tension. It's this. It's the net force that causes that. So now I'm going to solve for tension while accelerating up here. So if I look at this thing here, look what I'm going to do here. So when I look at this thing, numerically, what you're seeing here is that I have the following thing. Is that this says, so I'm going to call this equation 1. So now equation 1 tells me that the tension up must be the mass of mg plus ma. Note that we do not have the mass. So what I'm going to do here is that I'm going to do the following thing. I'm going to factor out the mass and note that this is g plus a. Now there's a couple ways that you can actually deal with this. Okay? So there's two ways to get the mass. One way is just calculate the mass. We know that the force of gravity, which is the weight, they tell us that that weight is what? It's 27.8. So this is 27.8 newtons. And we know this has to be mg. So this tells us here that I could get the weight by just calculating 27.8 newtons divided by 9.81 meters per second squared. And you can get it that way. I actually did not do it this way. What I did is I note that, look, I have mass. And mass is mass no matter what. But what happens if I come in here and I multiply and divide by g? I haven't done anything. I know the value of mg, it's 27.8, and of course I could put in by that. So what I end up doing when I do this calculation is that I literally come in here and I do this. I come into here and then I plug this guy into here, right? So here it is up. And now what I do is I replace the mass term like this. I go mg divided by g times g plus a. So then, what do I know about this whole thing? Well, I know mg is 27.8 kilonewtons, right? It better be kilonewtons. It can't be newtons. Yeah, I forgot to put in my kilonewtons right here. But remember, you got to be careful with the kilonewtons because it's going to be what? It's 27.8 times 10 to the 3 newtons. And then the acceleration is 1.22 meters per second squared. So then I come in with, and I just immediately write 27.8 times 10 to the 3 newtons divided by 9.81 meters per second squared. 9.81 plus 1.22 meters per second squared. And you could see here that that term and that term cancel out, leaving me newtons for the tension. And when I calculate the tension, I get 31,300 newtons or 31.3 kilonewtons, and that's my tension up. So I now have my tension going up here. Okay, so I'm going to come up and grab this guy, and I want to bring it back down. So I got, this is the tension required in the cable to accelerate this. Now note, does this make sense? The answer is yes, because we needed that the tension force was greater than the force of gravity. And we can see here that we have 31.3 kilonewtons is greater than the weight of 27.8 kilonewtons. So yes, the tension had to be greater than the weight, and that's what's making this thing accelerate. So here we go. Now what I want to do here is that I want to come in and I want to look at the next piece. And the next piece says, what is the tension when the elevator is accelerating, moving down? So, question, physically, what does the tension look like while accelerating downwards? What would you expect the tension to be if you are accelerating downwards? So if I look at a picture, draw a free body diagram. And here's my cable here. You now know that you are accelerating downwards. So if you are accelerating downwards, you know that the net force must be downwards. So the only way you could have a net force of being downwards is that look at the length of force of gravity. If I look at the length of force of gravity, it was what? 3 squares. So if it's 3 squares, look at my picture now. Gravity does not change. The elevator did not change. So the only way I can accelerate downwards is that what happens to the tension? It had to have decreased. It has to be smaller than the force of gravity. So if that's the case here, that means if you have an elevator accelerating in that direction, look at my sign convention. Look at my sign convention. What is the direction of velocity? It's down. I now switch signs. So here I go. If I go and I look at this thing, you could see the big difference here is that now gravity is positive and tension is negative. And what am I accelerating? Mass times acceleration. So what caused this thing to accelerate? It's mg minus tension. So what we're doing here is that we started looking at 6.1, and it says that we had an elevator with the weight of 27.8 kilonewtons, has an upward acceleration of 1.22 meters per second squared, and we want to calculate the tension in the cable. So this is what we did. We looked at this thing. We knew that it's accelerating, so that the net force had to be upwards. That immediately told us that in order to be going up and accelerating, that means that the net force is not zero, so I have unbalanced forces, which in our case tells us that the tension up must be greater than the weight of the elevator. Okay, and that's exactly what we were looking at here. So now what we want to do here is that from our free body diagram, what we're seeing here is that the tension up, we tried to draw larger than the weight down. So because the velocity is upwards, right? Because V is upwards, that implies choose positive to be up also. And that's important. So here we go. We write down the N2L equation that tells us the tension up minus the weight down. Of course, that's our net force. That's what's causing this thing to accelerate. Then we solve for the tension up and we get this relationship. So instead of solving for the mass, I said that I was going to divide and multiply by G. And so then if I plug in my values, we got a tension up that was 31.3 kilonewtons. Okay, so that's what it is. So now what we were doing next here is that we were going in and we were going to look at what happens when the elevator is accelerating downwards. If the elevator is accelerating downwards, then what that tells us here that the net force is not zero here. So again, I have unbalanced forces here. So that tells us in this scenario here that now mg is the opposite. But in this case here, I'm going to say that that's the tension where we're accelerating down. So that's what happens. So what we expect here is that mg should be exactly the same. So if it was 3 squares up here, it has to be 3 squares down. So that means you have to reduce the tension that's acting on this thing. Again, velocity direction is down. That tells me positive direction is down. So note, gravity in this case is positive. Gravity in this case was negative. And it's because we're using the velocity to tell us how to define that. So here we go. So now that I have this thing, then what I'm going to do here is that I'm going to go in, I'm going to do what? I'm now going to solve for T down. And note that I didn't write that down here, so I'll have that there. So now if I do that, you can see that I'm just going to do a little bit of algebra. So it tells me that T down is then going to be, in this case, it's going to be mg minus ma. Or again, I'm going to subtract the mass value out. I now have the tension here. So if I plug in my numbers, right, they're the same G, the same A, and I'm going to apply the same trick that I did up here. I'm just going to write in the number this time. So then this tells me numerically that if you compute this, I ended up getting 24,300 newtons, or I can write this as 24.3 kilonewtons. So when you're looking at this, I now have the tension. Okay, I now have the tension. And the thing that I want to do here is that, what do we know here? Okay, what do we know? Well, one, we calculated for so the first thing that we did here is that we looked at an elevator speeding up, going upwards, and that implies that the tension up, we saw that that value was what? I think it was 27, no, 31. So it's 31 point, okay, I still don't remember it, 31.3 kilonewtons. And then we looked at an elevator speeding up, going downwards. And if we compute that, what we're seeing here is that this number is 24.3 kilonewtons. So you could see that there's values like this. So the question is, what does this even mean here? So what I'm going to do here is that to make a comparison here is that I'm going to look at a stationary slash constant velocity moving elevator. So if we do that, what am I seeing here? So I have an elevator that's doing this. And so the thing that I want to look at here is what I'm seeing here is that if I do that, then this immediately tells me that I must have balanced forces. And if I have balanced forces, the only way this could be true here is that the force of gravity balances out the tension, right? It balances out the tension. And in this case, I'm going to just say stationary. And what we're finding here is that we already know what the weight is. So this tells us here that the tension, when it's stationary, must be the weight, but the weight we already know because it's given is 27.8 kilonewtons. So so the question that I'm really asking here is that I'm asking a physics question. why is T up greater than T stationary greater than T down? Well, there's a couple of reasons that we could think about here. Is that for starters here, note, imagine, so the question is that imagine a constant velocity elevator. So I'm thinking about this elevator. And all we know is that this guy is now moving at v equal to a constant. So that means here that the tension in this case where the velocity is equal to a constant must be 27.8 newtons. But note, if this is moving at constant velocity and now I try to accelerate that, I have to increase the tension, right? So this implies here is that one must increase the tension to make elevator move faster. And that's exactly what happens when you see this here. So what we're seeing here is that you can see that the tension going up is greater than the stationary. And that's the only way that you can make it go faster. Now, let's think about it in the opposite direction now. So if I'm thinking about the elevator going down, so note, when I'm going down, what's actually happening in this situation? Well, the elevator's already falling, okay? So in this scenario here, what we're gonna do here is that now imagine elevator is moving down at constant velocity. So when I'm looking at this scenario here, again, if I think about this scenario, what am I seeing here? Well, I'm seeing my elevator, and I have my tension here. Again, this tension, V equal to a constant, is 27.8 kilonewtons. And it's moving at V equal to a constant in this direction here. Now, since this is already moving in the direction of, the gravity is here, note that in this case, one does not have to push harder to make the elevator go faster, because it's already moving in that direction. In this other case here, you were going against gravity, right? The big issue here is that you're going against, now you're going with gravity. So as a consequence, you don't have to push as hard. So what you see here is that now, when I look at the stationary value, this guy is then going to be smaller than going down because you don't need to push as much. Whereas before, you're going against gravity, you have to push as much. So that's what it means when you're having these three values here. Now, what I want to do here is that I want to come in and I want to look at this example here. And the example that I want to continue to go on here is that if I look at this thing here, what I'm really focusing here is on this guy right here.